Hi guys. Today's lecture is going to be on algorithm analysis. Um, to recap, we've gone over some of the more rudimentary algorithms. In terms of searching, we've done linear search and binary search, as well as linear search through a linked list, so traversal through a linked list. We've also done sorting algorithms, selection sort, insertion sort, quick sort, merge sort, shelf sort. And so now, if you recall, oftentimes I talk about the efficiency of an algorithm. Whether one algorithm is more efficient under a certain condition. For example, insertion sort was more efficient when the array to be sorted is already nearly sorted. I also talk about efficiency in terms of, for example, linear search is not as efficient with a sorted array as binary search. Binary search is more efficient. And so the question becomes, how do we start to quantify this efficiency? How do we analyze the efficiency? And so that's what this lecture is going to be about today. So if we dive into the slides, to continue on with the recap, an algorithm is a sequence of steps for accomplishing some sort of task. So for example, searching, you were searching for some sort of value within some sort of collection. And in terms of sorting, what you're trying to do is rearrange the elements within some sort of collection or array to be in sorted order, whether that is ascending or descending. An algorithm's runtime is the time the algorithm takes to execute. So recall the Amazon example for, I believe it was 200 million items in Amazon's store. A linear search might take 3 minutes to find a particular item. So the runtime is 3 minutes there. Whereas binary search, assuming the items are sorted in Amazon's online store, a binary search might take only some number of microseconds. So another way that we looked at algorithms was in terms of the number of steps they took. So if we look at the sorting algorithms, right? The sorting algorithms sometimes were looked at in terms of the number of swaps that were made in order to complete the sorting algorithm, as well as the number of comparisons, right? And we also saw the number of comparisons or with the searching algorithms, we also saw the number of comparisons coming into play. And so looking at this example here, an algorithm typically uses a number of steps proportional to the size of the input. For example, for a list with 32 elements, linear search requires at most 32 comparisons. One comparison is only needed if the search key happens to be found at index 0. 2 comparisons are only required if the search key is found at index 1, and so on and so forth, up to 32 comparisons if the search key happens to not be found. So in other words, you've searched the entirety of the list, all 32 elements, and could not find the search key. And so basically, the number of steps that were taken, if it's one step per comparison, then essentially you've taken 32 steps in completing this algorithm. So now we talk about the number of steps proportional to the size of the input. If we change 32 elements to, say, 200 elements, then it's possible under that worst case scenario where we might have 200 comparisons or 200 steps. So that's what this number of steps proportional to the size of the input is addressing. And so yeah, we start to not looking at more specific numbers and more generalizing things. We want to look at, for a list with n elements, linear search thus requires at most n comparisons. So n being, just some number of elements. We don't know how large n is, but it's just some number. And the algorithm is said to require on the order of n comparisons. And so, okay, so now here we get into some of the terminology and definitions for algorithm analysis, upper and lower bounds. So, an algorithm with a runtime complexity T of n. So, before I continue, n being the same, some number of elements in some sort of array that you're going to work with, right? Whether you're searching or you're sorting or whatever, n is the number of elements. And the T of n is basically a function based on n. And it's a function that's going to compute the runtime, so how long it takes for a particular algorithm to run. And so this T of n has a lower bound and an upper bound. So looking at these bullet points here, T of n is a function representative of an algorithm's runtime as n grows. And so here's the lower bound and the upper bound. The lower bound is a function f of n, so it's a different function, that is less than or equal to the best case T of n for all values of n greater than or equal to 1. So for all values of n greater than or equal to 1, that sort of makes sense, right? Basically what we're saying is as long as there's at least one item inside of the collection or array that we're working with. But now the confusing part is, so a lower bound is a function f of n that is less than or equal to the best case T of n. So if T of n is a function that represents an algorithm's runtime as n grows, the best case would be when that runtime produced is extremely small. Or at least the growth compared to n is very low. And so a lower bound would be considered any function that's less than that best case scenario. And then the upper bound is the opposite of that. So it is a function, f of n, but it is a function that is greater than or equal to the worst case of T of n for all values of n greater than or equal to 1. So in the situation where the function representing the worst case of T of n, outputting based on the growth of n some very large runtime, an upper bound is a function that is greater than that function. And so yeah, remember n is the number of elements your algorithm might deal with. And so a lot of this, we care about the growth of n. We care about, as n goes from 3 elements to 32 elements to 200 elements to 200 million elements to a billion elements, right? How is our function, how is our algorithm performing? So we need to keep this in mind as we continue learning this analysis. So the best case of T of n means the behavior in which your algorithm experiences the smallest amount of runtime growth as n gets bigger. Now I can understand this might be a little confusing right now. And so a slightly less accurate but an easier way to slightly understand this might be the case in which the time it takes your algorithm to execute is at its smallest. In reality, the best case is mainly talking about the smallest amount of growth based on n. But this other less accurate definition is one way to begin thinking about how best case works. Worst case the opposite, so the behavior in which your algorithm experiences the largest amount of runtime growth as n gets bigger. And a less accurate but easier way to say this is the case in which the time it takes your algorithm to execute is at its largest. So, in strict mathematical terms, the upper and lower bounds are not the same as the best and worst case runtime complexities. They are definitely two different things. And we'll talk more about the differences in a second here. In the context of algorithm complexity analysis, the terms are often used to collectively bound all runtime complexities for an algorithm. Therefore, the terms are used in this section such that the upper bound is greater than or equal to the worst case, T of n, and the lower bound is less than or equal to the best case, T of n. So we'll look at an example here. And one thing that is interesting is, given a particular algorithm, your best case and your worst case can be two completely different functions. And so we'll go ahead and look at an example here. An algorithm's worst and best case runtimes are represented by the blue and purple curves respectively. So here's the blue, the worst case, and you'll notice here is your T of n for the worst case scenario. And you can see it's a completely different function than the T of n for the best case scenario. And so the idea is that your lower bound is going to be some function that is less than the best case. And your upper bound is going to be some function that's worse than the worst case in terms of growth. So how can we see growth? Well, looking at the graph here, growth is measured by how much this curve here is going to curve up. A lower growth curve, for example, for the lower bound, might be a very slow, gradual increase in the curve, whereas a more worst case curve is something that will drastically spike as n increases. So we'll go ahead and take a look at this. If we look at the algorithm runtime bounds, 2n squared, shown in yellow, is a lower bound. Now notice is a lower bound. It is not the lower bound. There can be multiple lower bounds. Just 2n squared is less than 2n squared plus 5n plus 5. And the lower bound is less than or equal to both runtime functions for all n greater than or equal to 1. And so now we choose the upper bound. 30n squared, shown in orange, is an upper bound. And the upper bound is greater than or equal to both runtime functions for all n is greater than or equal to 1. It's an upper bound. So once again, anything that's larger than the worst case will suffice. But in this case, 30n squared is chosen. And you can see 30n squared is drastically larger. So this is what I'm talking about. In terms of growth, as n gets bigger, the function for T of n is producing a runtime that's drastically getting larger and larger and larger. Whereas if we look at the yellow line here, the 2n squared, as n gets bigger, the runtime produced from this T of n function is much, much, much smaller. So if we run it one more time, together, the upper and lower bounds enclose all possible runtimes for this algorithm. And this is why we look at lower bound and upper bound, right? It suddenly gives us a range in which our algorithm might operate. So going back to the slides, an additional simplification can factor out the constant from a bounding function, leaving a function that categorizes the algorithm's growth rate. So, for example, instead of saying that the algorithm's runtime function is an upper bound, or has an upper bound, of 30n squared, the algorithm could be described as having a worst-case growth rate of n squared. And doing this is something called thinking in terms of asymptotic notation. So asymptotic notation is the classification of runtime complexity that uses functions that indicate only the growth rate of a bounding function. So asymptotic notation only cares about growth rate. It doesn't care about anything else about your functions. And so because all we care about is growth rate, all we're going to care about is the highest ordered terms of the functions. So there are three asymptotic notations that are commonly used in complexity analysis. There's actually more than this three, but these are the three we're going to go over in this particular slide. And then after this, we'll only focus on big O notation. So big O notation provides a growth rate for an algorithm's upper bound. So once again, an upper bound, as n gets bigger and bigger and bigger, how your T of n algorithm will take longer and longer and longer, as opposed to the best case, where it would take not as long. We have big omega notation, which provides a growth rate for an algorithm's lower bound. And we have theta notation, or big theta, which provides a growth rate that is both an upper and lower bound. Just so you know, the big O, big omega, and big theta, the opposite of these, which we aren't covering, is little o, little omega, and little theta. So we'll go ahead and take a look at the formal definition. We go back to Zybooks. Oops. And so this is the formal definition right here. So T of n is equal to big O of some function of n, namely the upper bound. For big omega, the T of n is then equal to big omega of the function of some function of n, which is the lower bound. And for theta, T of n is equal to theta of some function wherein both the lower bound and the upper bound have exactly the same growth rate. And so these are the formal definitions. For big O, a positive constant c exists such that for all n greater than or equal to 1, T of n is less than or equal to c times the function of n. For big omega, a positive constant c exists such that for all n is greater than or equal to 1, T of n is greater than or equal to c times that function of n. And then for theta, you can see the upper bound and the lower bound are equal, their growth rates are equal, and so you can see this by T of n is equal to big O of the function of n as well as big omega of the function of n. So going back to the slides, we'll go a little more in depth on big O. So big O notation is a mathematical way of describing how a function or the running time of an algorithm generally behaves in its relation to the input size. In big O notation, all functions that have the same growth rate as determined by the highest order term of the function are characterized using the same big O notation. What this is saying is basically, if your highest order term is 30n squared, this is the same in terms of big O notation, this is the same as 2n squared. And it's also the same as 100n squared. The reason why is because big O, or the asymptotic notation here, only cares about growth rate. And the growth rate is only determined by n, and in this case n squared, for the example. So in essence, all functions that have the same growth rate are considered equivalent in big O notation. So we'll go ahead and take a look at an example. Go back to Zybooks. Looking at the big O notation tab. So here we're determining, given some algorithm, find the big O notation. And so here's our algorithm. Here's the number of steps, right? And it's 5 plus 13 times n plus 7n squared. This is our algorithm. And big O notation, to start, we create a big O and wrap in parentheses the algorithm. And so what we're going to do is compute the big O notation. And so there's two rules to keep in mind here. The first one, if the function of n, which is this 5 plus 13n plus 7n squared, is a sum of several terms, the highest order term is kept and the others are discarded. So the highest order term in this case is 7n squared. It's highest order because of the n squared part. If there was an n cubed would be the higher order term. And so you can see here, n squared is a higher order term than just n. And n is a higher order term than not having an n at all. And so 7n squared is the highest order term, so that's all we're going to keep. And so you can see here big O of 7n squared. And once we've determined the highest order term, the next step is to apply rule 2. If a function has a term that is a product of several factors, all constants are omitted. So in other words, this 7 here is not necessary. And it's not necessary because, like I previously mentioned, big O, this asymptotic notation here, only cares about growth rate. And because of that, the constant can be removed. And so here we are, big O of n squared. And so all functions with the same growth rate are considered equivalent in big O notation. So anything on the order of n squared would be the same when, under big O notation. These are rules for determining big O notation of composite functions. We won't go over that right now. All right, going back to the slides. One consideration in evaluating algorithms is that the efficiency of the algorithm is most critical for large input sizes. Small inputs are likely to result in large running times. That's an error, small running times because n is small. So efficiency is less of a concern. Go ahead and fix that. And so what this is talking about is something that's fairly intuitive, right? If your array only contains 32 items and you're going to apply some sort of searching or sorting algorithm, it's going to be very fast. And so n is quite small. But how does it start to perform when you get to 200,000, 200 million, or 200 billion items? N starts to get very, very large. And so the large input sizes are what we care about. Small ones are basically negligible. And so we can see this, going back to Zybooks here. If we look here, this is the growth rates for different input sizes for different functions. We see here we have log of n, n log of n squared, n cubed, and lastly 2 to the nth power, or exponential. And this is in the order, this is in an increasing order. in terms of the higher order. So, for example, n cubed is a higher order than n squared, and n squared is a higher order than n log n, so on and so forth. And so these higher order terms, the reason why we care about them is because they tend to take the longest amount of runtime given larger input sizes. And so we can see this right here. If we look at just n, given an input size of 10 elements, n will only take or have a runtime of 10 microseconds. It's very fast. And if we jump all the way to the end here, we have n is equal to 100,000 elements, n only takes 100 milliseconds. Still very fast. But if we go up to a much higher order term, for example n cubed, n with only 10 elements takes 1 millisecond, not very long, fairly negligible. But as soon as we get to n is equal to 100,000, look at that, an n cubed algorithm might take 31.70 years to complete, which is ridiculous, absurdly long, right? And this is why we care about growth rates of algorithms. As n gets bigger, this particular higher order function is going to take a very long time to compute what we're looking for. And of course, you look at the exponential, the 2 to the nth power, starting off n equals 10, somewhat small, 0.001 seconds, but it's barely increasing n to n equals 50 will now increase it to 35.7 years, your runtime. And of course, get to anything beyond that and you get over 1,000 years, which isn't insane, right? Can you imagine trying to run your program for over 1,000 years? That doesn't make sense. And so this is why we care about growth rate and how growth rate affects different functions. So let's go back to the slides. And go back to Zybooks. So yeah, there are some very common big O complexities to look at. Right here, so you'll see on the left here of this chart, this table, we have the big O notation. Big O of 1 is how you write something that is constant. That means as n gets bigger and bigger and bigger, the affected runtime doesn't change. It's always going to be constant. And so you can see in code here that an if-else branch is something that might produce constant runtime. There is no n here, in other words. We look at big O of log n, this is considered logarithmic. And if we look at the function name here, interestingly, we've already gone through this, binary search. So yes, binary search runs at a big O of n complexity, runtime complexity. And so what this means is, as n gets bigger, the runtime is going to increasingly get small. Or the rate of growth will increasingly get small. Of course, it still takes longer each time as n gets bigger, but its growth rate is not getting very much larger. And we know this because binary search is halving the number of elements required to search through each time you go through the search. We look at linear search has a growth rate of big O of n, or runtime complexity of big O of n. And so what we notice here is the for loop here. This for loop is a large indicator of a big O of n complexity. So basically for, and we loop numbers, size, number of times. And then inside of it we complete a constant time operation. So this is linear. We see merge sort goes for n, big O of n log n, which is linear rhythmic. Big O of n squared, quadratic, selection sort. And so one way to tell big O of n squared, and we'll look at this in a second, is nested for loops within each other, and both of these for loops contingent on the number of elements. And then something exponential. For example, big O C of n, the Fibonacci sequence, which we're not going to worry about. So going back to the slides. So how do we analyze these different algorithms? And to analyze how the runtime of an algorithm scales as the input size increases, we first determine how many operations the algorithm executes for a specific input size, n. Then the big O notation for that function is determined. We'll look at an example of this in a second here. The algorithm runtime analysis often focuses on the worst case runtime complexity, which is why we're looking at big O notation. The worst case, or big O notation of the worst case scenario. And the worst case runtime of an algorithm is the runtime complexity for an input that results in the longest execution. So yeah, and other runtime analyses include best case runtime and average case runtime. And determining the average case runtime requires knowledge of the statistical properties of the expected data inputs. In other words, usually calculating average case runtime requires some beforehand knowledge, which is unrealistic. And best case runtime is generally not very useful. So this is why we as computer scientists truly care about worst case runtime complexity. So in other words, under what conditions will our algorithm run or take the longest to run? So we'll go ahead and take a look at determining worst case runtime. Going back to Zybooks. So in this first example, we're going to do a runtime analysis. This particular for loop here is finding the maximum value in some sort of array. And what it's going to start off doing is counting the number of operations. So we'll go ahead and start this. Runtime analysis determines the total number of operations. Operations include assignment, addition, comparison. Pretty much anything is considered an operation. So we assign max val to number 0. This is an operation. We have this for loop. The I equals 0 inside of the for loop is an operation. It only gets executed once. And the for loop is going to loop n number of times. For each loop iteration, we increment the I variable and make a comparison to check and see if I is less than n. Both of those are operations. And so that's why this two operations here is a subsection under n iterations. And then within the for loop, we have an if statement that compares the maximum value with the current value that we're looking at inside of the array. That is an operation. And then we have this assignment line right here, and that is also an operation. And what you'll notice is that this is represented by the two operations and then parentheses worst case. Why is this the worst case? Well, and this brings up a good point on how this is a very easy example, right? But in a more complex algorithm, your best case and your worst case scenarios might produce two different functions. And the reason being is, if we look here, the worst case scenario is when a number is indeed greater than the max value. This if statement evaluates to true, which means we now have a completely extra added operation to our algorithm. And this can generate different functions. And so here we go, we have a final comparison. Once the for loop is finished, we have a final comparison of I is less than n to determine that the for loop is finished. And here we can now calculate the number of operations it took for our function to run under the worst case scenario. And so the first operation takes 1, the second operation takes 2, and then this 1 right here is from the final operation. They added those constants together, and then here the n times 2 plus 2 is because the n loops, or the for loop loops n number of times. And so here's the calculation, right? We have 3 plus 4 to the n, or 4n, and then we take the big O notation of this function, in which we apply rule 1, or we pick the higher order term, which is 4n, and then we strip all constants away, so we get rid of the 4, and then that's how we come to the conclusion of big O of n. And so we can do this again. Another way, so this is counting the number of operations, right? Another way to do the runtime analysis is to apply the big O of 1 constant runtime complexity to large sections of constant operations. So what does that mean? Well, basically what they do is they lump together all of these constant operations here into one big O of 1. And then same with these, of course, operations to the top and bottom of the for loop. And so what happens is you have big O of 1 for the top one, big O of 1, or constant time for the bottom one, and the for loop is n times big O of 1, which results in big O of n. So going back to the slides. Constant time operations for algorithm. So for algorithm analysis, the definition of a single operation does not need to be precise. An operation can be any statement or constant number of statements that has a constant runtime complexity of big O of 1. And that was pretty much any comparison or any assignment operator. Those are statements that have a runtime complexity of big O of 1. Since constants are omitted in big O notation, any constant number of constant time operations is big O of 1. And so precisely counting the number of constant time operations in a finite sequence is not needed. In other words, what they're saying is we can just lump together all of the finite, or all of the constant statements as just big O of 1. So we can look at the runtime analysis of nested loops. Why nested loops? Well, as it turns out, nested loops produce a larger growth rate. And so the runtime analysis for nested loops requires summing the runtime of the inner loop over each outer loop iteration. And then the resulting summation can be simplified to determine the big O notation. So we'll look at an example of this on Zybooks. So here we are, runtime analysis of a nested loop. We're looking at the selection sort algorithm. And if we remember, the selection sort algorithm has a for loop within a for loop. And so what this means is, at each iteration of this outer one, the inner one will loop n number of times. And the outer one will also loop n number of times. And so as we watch this run, right, for each iteration of the outer loop, the runtime of the inner loop is determined and added together to form a summation. And for iteration I equals 0, the inner loop executes n minus 1 iterations. And as I increments, we still loop n minus 2 iterations because j is based on I. And this continues until eventually we only loop 1 or 0 times. So I'm going to let this finish. And so here we have it. We have so you'll see n minus 1 plus n minus 2 plus n minus 3, so on and so forth, until eventually you get plus 2 plus 1 plus 0. And this actually mathematically is a series, a summation series. And we can convert this into n times n minus 1 over 2. And so this is the function representing the selection sort algorithm here. And so the next job is to convert this, to apply big O notation to this. And so how are we going to do that? Well, we can multiply the n into the parentheses, so we'll get n squared minus n over 2. And then when applying big O notation, we'll pick the highest order term, which would be n squared over 2. And then we can remove all constants, finishing off the big O notation at n squared, big O of n squared. And then so all they're doing here is essentially the same thing I was talking about before. So they solve for the big O notation here, which ends up being big O of n squared. and yeah, we can see that right here as well. So going back to the lecture slides, we can now look at the runtime complexity for the different searching and sorting algorithms that we had previously covered. So we'll go back to Zybooks. We already talked about the, let me see, we saw that binary search was, where are they? Look at the fast sorting algorithms. So we already saw the searching algorithms runtime complexity. We saw linear search was big O of n, and binary search was log n, big O of log n. So we'll go ahead and look at the different sorting algorithms here. Now what we're looking at here is the average case, right? So this is big O of the average case, which gives us big O of n squared for selection sort, big O of n squared for insertion sort, big O for shell sort, big O of n to the 1.5. Now why is this less than n squared? Well, if you recall, insertion sort under its best case is more efficient and performs better when the elements are already in nearly sorted order. And so this is why shell sort is slightly more efficient than insertion and selection sort. You have quicksort, which is big O of n log n, merge sort, which we've already seen, which is big O of n log n, and we didn't cover heap sort or radix sort. Once again though, this is the average case, and we don't actually care so much about the average case, we really care about the worst case. So we'll look down here, and if we look at the best, so here they're only showing quicksort and merge sort, and we're looking at the best case and the average case and the worst case of these algorithms. And looking at quicksort, while in the best and average case, does perform at big O of n log n. Its worst case, as we can see, is big O of n squared. Now why might this be? Well, as it turns out, if you recall, quicksort uses that pivot value, right? Well, if you choose a pivot value that's on either end of the array, and if your array is sorted in ascending or descending order, or all of the elements are exactly the same in your array, this provides the conditions for Quicksort's worst case runtime. And as it turns out, under the worst case, Quicksort will perform at big O of n squared. And so this is why now we look at merge sort, and it's actually impressive that merge sort is big O of n log n across the board, even in the worst case scenario. All right. And that's all I have for you for this lecture.